Hi, today we're going to talk about electrolysis. So before we get into electrolysis, let's quickly review reversible reactions. If you have a reaction like the combustion of methane, and you know that the products are favored at equilibrium, that tells you that the forward reaction is favored, it's a spontaneous reaction, and the reverse reaction is non-spontaneous, it's not favored. So is it possible to get the reverse reaction to happen? Well, it is. We can do that by putting a lot of energy into the reverse reaction, thereby getting reactants out. So now let's think about another reaction, this one an electrochemical reaction. If you have potassium chloride, which splits into potassium plus ions and chloride ions, and you wanted that to turn into solid potassium metal and chloride gas, first question we have to ask is the forward reaction spontaneous? Well, if you look at the cell potential, which is minus 4.89 volts, the answer is definitely not. How about the reverse reaction? Is that spontaneous? Well, sure. If the forward reaction is not spontaneous, then the reverse reaction would be spontaneous. So is there a way that we can get the forward reaction to occur? As before, the answer is yes. And the way that we do that is by putting in a lot of energy. In this case, because it is an electrochemical reaction, the easiest way to do that is with the application of electric current. The answer is yes, and it's through the process of electrolysis. Electrolysis is basically an electrochemical process that basically allows non-spontaneous reactions to occur. And as with other non-spontaneous reactions we've talked about before, that happens by putting a lot of energy in. And in this particular case, that energy is applied in the form of an electric current. Electrolysis takes place in what we call an electrolytic cell. And in many ways, electrolytic cells are the opposite of what we would call a galvanic cell. If we look at our cell here, we see an anode where oxidation occurs. That is actually the definition of an anode. It's the electrode where oxidation occurs. And then we have our cathode where reduction occurs. But this is very different from a galvanic cell in that our anode has a positive charge, whereas in a galvanic cell it would have a negative charge. Our cathode has a negative charge. So let's look at how this electrolytic cell could be used to turn potassium and chloride ions into potassium metal and chlorine gas. So you have a positively charged anode, and that will attract negatively charged ions. In this case, that would be chloride. The chloride ions would then lose electrons, which would travel through the electrode into the wire. And as the electrons kept traveling around, they're going to make their way to the cathode. That's how it acquires its negative charge. And that negative charge will attract the positively charged ions like the potassium. The potassium can then accept some of those electrons to form potassium metal. As I said before, all of this happens because there is a source of electric current that is pushing electrons to the negatively charged cathode. Now, the electrodes are not the only thing about the electrolytic cell that is different from the galvanic cell. If you remember, our galvanic cell had two different chambers. There was one solution with the electrode that formed the anode, and there was one electrode in a separate chamber in a solution that was in contact with a cathode, and then we had the salt bridge in between them. So electrolytic cells always have both the anode and the cathode in one chamber, and that allows the migration of positively and negatively charged molecules or ions to migrate to the various electrodes. The technology of electrolysis is used for many things. One of them is a process that we call electroplating, in which you're putting a metal coating onto a surface. It's used to create pure metals like potassium, which don't generally occur in nature. And also it's used in rechargeable batteries. So normally the way people do electrolysis when they're trying to make metals like sodium or potassium that don't occur in nature is they actually just put salt in a large heat-proof container and they melt it. So obviously this would have to happen at very high temperatures. And so, as I said before, the anode is going to attract the negative ions. As those negative ions transfer electrons to the anode, they get oxidized. The cathode is going to attract the positive ions, and it has a negative charge because it has extra electrons flowing into it, and therefore can help to reduce the positive ions that are attracted to it. So you might wonder why it is that people melt a salt if they're going to try and electrolyze it. Why don't they just put it in water? Which is a very good question. So we have to think about how electrolysis would take place if we had an aqueous solution. So remember that the anode, which is positively charged, will attract anything that has a negative charge, and so that could be chloride ions. It also could be water, because remember, water molecules have a partial positive and partial negative charge on either end. And so the water molecules could be oxidized by the anode, not just the chloride. Likewise, the cathode could attract anything with a positive charge, which could include the positive end of the water dipole, so that would be the end with the hydrogen atoms. And then if that was true, then the water molecules would be reduced by the cathode. So how do you know which will happen? What you have to do is you have to look at the cation that you're trying to reduce and water. So if you're trying to reduce sodium, for example, the standard reduction potential of that is negative 2.71 volts. And if you're trying to reduce water, which would produce hydrogen gas and hydroxide, the standard reduction potential for that is negative 0.83 volts. I want you to think back to what we said about standard reduction potentials. And if you'll remember, the largest cell potential, or another way to say that is the most positive cell potential, is going to be the one that is most likely to be reduced. So if you have multiple possible reactions within an electrolytic cell, you're going to look at which of those reactions has the larger standard reduction potential, and that is the one that is going to happen. So in this particular case, it is easier for the system to reduce water to hydrogen gas and hydroxide than it is to reduce sodium ions to sodium metal. You could do the same sort of thing with your anions. Here you're looking at what's going to be oxidized. And here we have water possibly being oxidized to oxygen and 4H plus and 4 electrons, or to chlorides being oxidized to chlorine gas and 2 electrons. And once again, we're going to look at our standard reduction potentials. Remember that the smaller the standard reduction potential, the more likely something is to be oxidized. So we'll compare our half reactions, find the reaction with a smaller or more negative standard reduction potential. And in this case, that is water. So water is more likely to be oxidized than chloride ions. And so in that cell, what we would see is we would see water being both oxidized and reduced, whereas sodium and chloride would just remain unchanged. When you are doing electrolysis in an aqueous system, you will get hydrogen gas and hydroxide ions forming at the cathode. You'll get oxygen gas and H plus ions forming at the anode. And so the H plus and the OH minus will cancel each other out, so the solution won't get too acidic or too basic, but you will be producing hydrogen gas and oxygen gas. And this is what a lot of people refer to as splitting water, a process which requires a lot of energy input. And so if you say, hey, we should have everything run on hydrogen gas, right now, the best way we know to make hydrogen gas is to run electricity through water. So that takes a lot of energy, and it's not really cost effective for running cars. So for the last part of this video, we're going to talk about the stoichiometry of running electrolysis. And really, understanding stoichiometry means thinking about the half reactions that are taking place as you run the electrolytic process. And you'll notice that all of these half reactions have an exchange of electrons, and that ends up being very important because it tells us how much electricity we need to run our reaction. So we do have to talk a little bit about units related to electricity. One you're going to see a lot is the ampere, which tells us how much electric current is flowing past a particular point. And the way that we measure amperes is linked to how much charge is passing that particular point at any given time. So the coulomb is the unit of charge. We've talked about coulombs before in relation to volts. Remember, a volt is a joule per coulomb. So basically, if 1 coulomb of charge flows past a particular point in 1 second, that is an ampere of current. But still, this doesn't tell us how things relate to moles, which is what we're going to need. And to get back to moles, we need to understand Faraday's constant. Remember, the units on Faraday's constant were coulombs per mole of electrons. So what that means is 1 mole of electrons has the equivalent of Faraday's constant worth of coulombs in charge. That information put together with what I showed you on the previous slide is how we're going to convert from electric units to moles of electrons. So when you're doing stoichiometry for electrolysis, it's going to work pretty much the same way that all stoichiometry works, and that you need a balanced equation for start. And that balanced equation is generally going to be for a 1/2 reaction, not the entire overall redox reaction. And then you're just going to go through from a known quantity of something you measured, convert that to moles, use the mole ratio, and then take the moles of whatever you converted it to a quantity that you can measure. What's different between this and the stoichiometry you've done in the past is that in either steps 2 or 4, you are probably going to be converting current and time into moles of electrons. This will only happen for one of those 2 steps, and the other one will probably be grams to moles or something like that. So let's try a couple of different problems here. The first one asks how many grams of product we'll get, specifically sodium metal, and we're given the amount of current that's passing through our molten sodium chloride and how long we're passing that current through. So the first thing we have to do is to write a balanced equation. So we're trying to make sodium metal, and we're going to do that by reducing sodium ions to sodium metal. Now we're going to convert the known quantity we're given in the problem to moles of something. And if you look at what we're given, all we're really given is an amount of current and a time. So 3.50 amperes times 12 minutes. And remember, we want to get this in terms of coulombs, which is amperes times seconds. And we have minutes. So let's convert our minutes to seconds. And that will give us 2,520 ampere seconds. Remember that ampere seconds means a coulomb, so that's 2,520 coulombs. And now we can use Faraday's constant to convert coulombs into moles of electrons. So now we have 0.0261 moles of electrons that are passing through our solution during these 12 minutes. Now we can use the mole ratio from our balanced equation to figure out how many moles of sodium that represents. We have a 1-to-1 ratio, 1 mole of sodium from every mole of electrons that flows through. So then we have 0.0261 moles of sodium, but we aren't asked how many moles of sodium we make, we're asked how many grams. So let's convert our moles of sodium to grams of sodium. And to do that, we're just going to use the molar mass, and that gives us 0.600 grams of sodium. Our next problem is sort of going the other way. We're given a mass of magnesium metal that we want to create, and we want to figure out how long we need to run our current through the molten magnesium chloride solution in order to get that mass of magnesium metal. So let's start by writing a balanced equation for electrolysis. Because we're trying to make magnesium metal, we're going to reduce magnesium 2+ ions to magnesium metal. Now let's convert our known quantity to moles. And the quantity that we know is 52.4 grams of magnesium. That's what we want to get. And we will convert that to moles by using the molar mass of magnesium. And that gives us 2.16 moles of magnesium. Now we're going to use our mole ratio from the balanced equation. We're trying to figure out how much electric current, so we need to find the ratio between magnesium metal and electrons. And so let's multiply our moles of magnesium by our mole ratio of 2 moles of electrons per mole of magnesium. and that gives us 4.32 moles of electrons. Now we want to convert those moles of electrons to something we can measure, and usually what we measure is we're measuring a combination of current and time. We're given the current, so we basically need to find the time. Here are the moles of electrons. So let's multiply our moles of electrons by Faraday's constant. And notice instead of putting 96,500 coulombs per mole of electrons, I just put amperes times seconds, because that's what coulombs are. And you'll notice that if we check our units, we're going to end up with units of amperes per seconds. Well, we just want to figure out how much time, so we just want to end up with seconds. Let's divide by the current that we know, 12.20 amperes, because then our amperes will cancel and we'll just end up with units of seconds. And in fact, it's going to take 34,170 seconds. That's a long time, and people usually don't talk about seconds when they're talking that much time. So why don't we convert that into a unit of measure that is a little more appropriate? I think 9.49 hours, basically 9.5 hours, is what we're talking about. That's something that people can relate to. The process of electrolysis is very commonly used in modern society for rechargeable batteries, for production of metals that do not naturally occur in the environment in their pure state, and many other processes. I hope this was helpful, and I will see you again soon.